In this video, we will run a regression analysis in R and also check some of the assumptions of regression. So first we just need to do our basic setup. We just have one additional package to load, which is the quant-psych package. And then we will read in our data. We're using the U.S. air pollution data set again. And then we can run our regression model. So first we're just going to run the basic model. So this piece, model 1, we can call this whatever we want. Model 1 seems pretty straightforward. And then into that we're going to use the linear model. That's what the LM stands for. SO2, that's the variable we're predicting, the tilde sign, and then it's predicted from manufacturing, and then tell it the name of the data set. And so when we run just this line by itself, we don't get any output. We have to ask for a summary of model 1 to get the output and the results. And so we get quite a bit of information. It just repeats what the linear model was, tells you the residuals, don't really need to worry too much about that. The coefficients, this is the most important part of the output, and you get several different types of information. So you get the estimate. The estimate for the intercept, that's the A value in the regression equation, so that's the y-intercept. And then the second one, so man-u, all right, this was our predictor variable, so this will always be labeled with whatever your predictor variable is. And then the value for estimate there, that's your regression coefficient or your slope or your B value. And then standard error, and we talked about standard error in class, and this is not the standard error you would typically report, but the standard error for that specific estimate. So it's not for the regression as a whole. T-value isn't actually the T-value like we usually think of it, but T stands for test, so this is just the test value. And then these are our p-values. And it puts asterisks in terms of the significance codes that are listed down here. So we see that our intercept is statistically significant. That's not something that we typically care about, whether our intercept differs from 0, but R will tell you that. What we really want to know is if our slope is statistically significant, and in this case it is. So manufacturing is a statistically significant predictor of SO2 levels. And then down here, what we really want to pay attention down here is the first thing, this residual standard error of 18.17. This is that overall standard error of the estimate that you might want to report. It tells you how many degrees of freedom you have. So your multiple r squared is the same as the little r squared that we talked about because there's only a single predictor. Once you have more than one predictor, then those would not be the same, and that tells you the variance in y that's explained by x. So in this case, the variance in SO2 levels, that's explained by manufacturing. And then again, it tells you degrees of freedom and a p-value for your overall regression. And notice that this p-value down here matches your p-value here. So really it's focused on your slope, not on your intercept. You can also use this option here to exclude any cases with missing data. So NA is sort of the notation that R uses for missing data. And so the action we want to take for NA is to exclude those. And so I just used model 2 instead of model 1, so instead of writing over model 1, it will create a new object to put that in, and then again you have to run the summary statement to get that output. In this case we don't have any missing data, so our results are exactly the same, but if you had missing data and wanted to exclude it, that's how you would do that. And then you can also get standardized coefficients as a function from the quant-psych package. So the function is lm.beta, and then you have to run the model first to get the unstandardized coefficients, which is what we looked at in the results before, and then you do the lm.beta with that model to get the standardized coefficient, and that's all it gives you is the standardized coefficient for the predictor variable, so 0.64. And so interpreting a standardized coefficient, these are in terms of standard deviation units. So a 1 standard deviation unit increase in the manufacturing variable would predict a 0.65 standard deviation increase in our outcome variable of SO2. And then we can calculate confidence intervals for our slope, and this uses a function in the quant_site package, which is just CONFINT, so confidence intervals, of model 1, because that was what we called the object that we put our linear model into. So those need to match. So if we run this, it will tell you your confidence intervals for both your intercept. Again, we usually don't care about this. The one we care about is the confidence intervals for manufacturing. Right, so our lower limit is 0.02 to an upper limit of 0.04. So even though it's close to 0, that's a pretty tight confidence interval. So that's a pretty good prediction. And then the last thing we're going to talk about is checking assumptions, and it seems like this is something that we should do before we run our model, but you have to have the model already run in order to check the assumptions. So there's this nice function plot that actually creates 4 different figures. So if we run just that, we get the 4 figures right here. Let's go to the first one. So this is our residual values, so the difference between the predicted values of y and the observed values of y, and then just those fitted values. And so in this, what we want to see is that the points should not have any structure or pattern. So they shouldn't be more spread out here and less spread out on the other end. And then also the scatter should not increase or decrease as the fitted values get bigger. So as you can see, there's some non-normality going on here, maybe partly because we just don't have very many data points that are this high up. And then we can look at the normal QQ plot. I actually think this one is about the most useful. So what you want is for all of the data points to be on this line. And data points that are far away from the line are outliers. So this looks like an outlier right up here. Next we have the scale location plot. And this is similar to the residuals versus fitted plot, but it uses the square root of the standardized residuals instead of just the standardized residuals. So it's basically the same thing. And the points should be along the line. So we can see that there are some points that are very far away. So notice this 7 up here is very far away from the line, and 7 over here is also an outlier. So we have a couple of indications that there's something weird going on with our 7th observation. And then the final one is the residuals versus leverage plot. And you can use this to see which of the y values have the biggest effect on the parameter estimates. Again, we see 7 sort of way out here having more influence than it should, probably because it looks like a bit of an outlier. Okay, another thing that we can do is to create a histogram to check for the normality of the distribution of residuals, and we can put a normal curve on that to really help us see how well that is normally distributed. So the first thing we have to do is create the studentized residuals, which are like standardized residuals, but they ignore the current data point. So we run that piece first, and then we use that to create our histogram. And so this portion of it will create the histogram. So if we do that, we'll get a histogram. And then this portion will create the normal curve. But if you click just on that, it won't work. We had something similar in the last lab where you have to have all of this together and then it will work. And then it will give you your histogram with the normal curve. So we can see we kind of have more people at this residual than we should. We kind of have some outliers up here. So really all of our plots and then this histogram are telling us that we do have some outliers in the data.